Hello all, this is the first video on solutions. It's an introduction. And on this video, we're going to talk about solutions and we're going to go over Blue Workbook pages 53 to 55. So we are going to go over and explain what solutions are. And we're going to say that, I'm going to remind you that solutions are homogeneous mixtures. And whenever you see a chemical with the word AQ, that means that it's a solution. And a solution automatically, it is a homogeneous mixture. What is solution made up of? Well, solution is made up of two parts, okay, that they're physically mixed. The one part is the solute and the other part is the solvent. The solute is always the smaller part. The solvent is the larger part, and I will explain what that means. The solute is the one part that is dissolved. The solvent is the one that does the dissolving. So, for example, if I have, and let me change, NaCl aqueous. Now, I know that this is a solution because it is a mixture. It is this chemical in water. It wouldn't be a mixture, it would be a compound if it was solid or if it was liquid. The moment I have, so those are just compounds, pure compound. Whenever we say AQ, that means that in the water, I have water and I added NaCl. That's why it's a mixture. They're physically mixed. So which one is the solute? What gets dissolved? Well, the salt. Specifically, NaCl is the solute. And what does the dissolving? Well, the water. That's why water is a solvent. And it's the larger part. And that's why water, we also call it the universal solvent. It dissolves almost everything. Not everything, almost everything. So whenever we see aqueous, that means that it's a solution. That chemical is added into water. It's a physical mixture. It's physically mixed. And it's a homogeneous mixture. What does homogeneous mix means? You cannot see the different parts. And imagine, take a glass of water, add salt, stir it. Can you see the different parts? No, cannot see different parts. Now we can have different types of mixtures. We can have, let's say, a solid into a liquid, okay? So the solid into a liquid. Now the solution is always going to take the phase of the solvent. So for example, when I add salt into liquid water, the phase of the solution is going to be liquid. Why? Because it's the solvent, it's the larger part that determines the phase of the solution. So how about if I have gas, for example, carbon dioxide gas into liquid water? What is the phase of that solution? Again, that is going to be liquid. An example is seltzer water. If I take water and I add carbon dioxide gas, it's going to be a mixture. It's going to be a solution of what? Water and carbon dioxide. What is going to be the phase of the solution? It's going to be liquid. How about if I have a solid into a solid? Well, that could be, for example, carbon into iron. That would be, what would be the phase? That would be solid. An example of that is alloy of metals. What are alloys? Alloys are mixtures mixtures of different metals, okay? There are different types of alloys, and metals become stronger. Or I can have iron and copper. They make it different. How about if I have gas into a gas? Well, what would be the phase of the solution? The phase of the solution would be gas. That's our air. For example, oxygen. Okay, what is the majority of the air? Well, we have nitrogen and so on. So the mixture of that solution would be a gas. Now, let's see what happens when we have aqueous solutions. Those are the ones that we're going to study. So let's move on. And when I have, let's say, NaCl, let's start with NaCl. And NaCl is added into water. The moment that it's added into water, and you can show it like this, or you can show NaCl is added into water. Either way is the right way. What happens is it breaks down into ions. It makes Na plus and Cl minus. Why does it break into ions? Well, it breaks into ions because this is an ionic solid. It's made up of a metal and a nonmetal. And we know from the formula, right, and the periodic table, sodium is a group 1, it has +1. Chlorine is a group 17, it has -1. So it's going to break down into ions. Now, what part is the solute? Well, the solute would be the NaCl. Okay, that would be the solute. The solvent would be, where is it added? Well, it's added into water. It's the larger part, and it breaks down. And we're going to do more examples on page 53 of the blue workbook. The next thing that we have to talk about is factors of solubility. We're going to talk about what affects solubility. What is solubility? Well, think about the word. Solubility means if something dissolves, if something is soluble in water. Well, there are different factors, and we can see those in our orange workbook. Okay, so let's see, let's annotate. Okay, so solubility means how much a solvent will dissolve in a certain amount. I mean, a solute will dissolve in a certain amount of solvent at a specific temperature. So what affects solubility? If something dissolves, is soluble. If something doesn't dissolve, is insoluble. Well, the first thing that affects is the nature of the solute and the solvent. So what does that mean? Okay, what I want you to know is that like dissolves like. Okay, so what does that mean? And I want you to remember it, and I want you to write these notes in your book, in the orange workbook. So I want you to remember like dissolves like. And what does that mean is polar dissolves polar, and then non-polar dissolves non-polar. So when they say the nature of solute and solvent, what they mean is that if a substance, so what do we have in a solution? Well, we have the solute and the solvent. For those two to mix, the solute and the solvent have to have similar polarity. Similar polarity. So solute and solvent have to have similar polarity. What does that mean? they have to, what does that mean that they have similar polarity, the solute and the solvent? That means that they are soluble. That means that one dissolves in the other. If the solute is nonpolar, then if the solvent, so we have different combinations. Let's go ahead and do these combinations. So solute, solvent, soluble or insoluble. So if my solute is polar and my solvent is polar, the solution is going to be, the solute is going to dissolve, therefore it's going to be soluble. So for example, my solute is NaCl. My solvent is water. The solute, the salt, NaCl, is soluble in water. Let's say my solute is nonpolar and my solvent is polar. What is that going to be? Do they have similar polarity like they had over here? No, that means that it's going to be insoluble. Let's give an example, the solute. Let's say oil is a nonpolar and water is polar. Oil is insoluble in water. Why? Because they have different polarities, and that's why they separate, they don't mix, you have to shake them. So water is going to be on the bottom because it has a higher density, and oil is going to be on the top. So they're going to separate, they're going to be insoluble. Or another word is immiscible, not mixable. The oil is not going to dissolve, it's going to be insoluble. And what does that mean, immiscible? They don't mix. So that is what this chart is talking about, the nature of the solvent. If one is polar and the other one is nonpolar, then it's going to be, if they're both nonpolar, it's going to be soluble. If one is polar and the other one is nonpolar, they're going to be insoluble. Let's move on to the next one. So the temperature, as the temperature increases, more solids become more soluble. That's true, and we can see it on table G later on. Okay, think about it. You take a glass of water, you add salt, it's dissolving. Some of it will not dissolve. Well, if you heat up the water, what's going to happen to the salt? It's going to dissolve. But however, gases have the opposite manners. So you have to remember, as the temperature increases, more solids become more soluble, but gases become less soluble. Pressure only affects gases, not solids, not liquids. As the pressure increases, the solubility of the gas increases. So let's see that. So pressure has no effect on solids or liquids, but as the pressure increases, the solubility of gases in liquids increase. So let's go ahead and start working on these pages. These are definitions that you're going to find in your orange workbook. So make sure you look at the orange workbook and you write down the definitions. There throughout the chapter or at the end of the book, there is a glossary. So let's start with this one, the solute and the solvent. Okay, so this is a solution. Which one is my solute? The formula name and the name. Well, it's MgBr2, and the name, it's an ionic compound. It's magnesium bromide. The The solvent is the one that does the dissolving, okay? The solute gets dissolved. The solvent does the dissolving. And that would be water. We know that from aqueous, aqua, water. Which one is the solute? Well, let's change the color so that it's K2SO4. That is potassium sulfate. Let's review naming. And the solvent is water. Which one is the solute? The one that gets dissolved. It's ammonium carbonate. And the solvent is water. Now we have to write the formula. So let's see. Let's do some groundwork. We have iron 3. Iron 3 means that you have the +3 because iron exists if we go on the periodic table +2 and +3. And we have chloride. It's -1. We know we can find this on the reference table, on the periodic table. So we're going to do the crisscross. And we are going to see that it's going to be Fe1Cl3. So the solution is going to be over here, FeCl3. Let me just use a different marker color. So it's going to be FeCl3, and my solvent, it's still going to be water. Copper 2 sulfate. Copper 2 is Cu+2. Sulfate is a polyatomic ion from table E. Sulfate is over here. So if we go back to this one, we're going to see that it's copper +2 and sulfate. And when I do the drawing, the +2 and the sulfate, remember I always circle the top charges and I say if I can simplify them. And I can simplify them by dividing them both by 2. Therefore, it's going to be +1 - 1. And the formula is going to be CuSO4. And the solvent is still going to be water. And then we have barium nitrate. Barium is +2. It's a group 2. Nitrate from table E is -1. I will do the crisscross, and it's going to be Ba parentheses NO3 2, and my solvent is water. Let's go on to the next page. It's what we did in the book. List the 3 factors that can affect the solubility of a substance. Well, we said the 3 factors that can affect the solubility of the substance from the orange workbook was nature of solvent, nature of solute, I should say, and solvent. Like dissolves like. They both have to be polar or they both have to be non-polar in order for them to dissolve. They have to have similar polarity. We have to have the temperature. The greater the temperature, the greater the solubility. That's true for solids, not for gases. And the final one is pressure, and pressure only affects gases. How does the temperature affect the solubility? What did we say? The higher the temperature, the higher the solubility. And we are going to talk about it later on table G. That's for solids. How does the temperature affect the solubility of a gas? Well, it has the opposite effect. As the temperature increases, the solubility decreases. How does the pressure affect the solid? No effect. It doesn't affect. How does the pressure affect the solubility of a gas? As the pressure increases, solubility increases. How do you think they make seltzer? They take water in a big, big tank. They add carbon dioxide on top, and they have a big piston that they move it down. And as they move it down, the carbon dioxide gas has no place to go than where? Into the water. That's how they make carbonated water, seltzer. What type of substance is water? Well, we know from bonding water is a polar substance. What type of substances or solutes dissolve well in water? Like dissolves like. If water is polar, we have to say polar substances. So that would be similar polarities because they have similar polarities. Or you can say like dissolves like. Now, let's go to table G. What we talked about the temperature is over here. We are going to see table G. And you can see it over here. And you can see it's the solubility of any chemical in water, specifically 100 grams of water, and they measure the temperature. So let's go ahead and see what's happening with all of this. We see Ki is an ionic solid. What happens to the solubility as the temperature increases? As the temperature increases, what does that mean? More and more and more solid can dissolve in what? 100 grams of water. What happens to this one? This one corresponds to what? NaNO3. What happens to the solubility of solids as the temperature increases? Well, as the temperature increases, the solubility of the solids in waters increase. That is for solids, for ionic compounds. However, some increase more than others. We have 1, 2, 3 graphs that don't agree with this one. We see it's this one. What does this one correspond? HCl. It is this one. That's an H3, and it's SO2. What I want you to know is HCl, NH3, and SO2 are gases. So let's go ahead and see. As temperature increases, the solubility increases for who? For solids. That's why they have a positive curve. But for gases, as temperature increases, the solubility decreases. That's why they have a negative curve. Which are the 3 gases? Well, it's HCl, NH3, SO2. You don't have to memorize them. They're all over here. Let's clear all the drawings. You should write this on your reference table. You shouldn't underline or highlight the three gases, not the solids. Okay. Below, solids that dissolve in water are given to the left. 4 different temperature and pressure values are given. Answer the questions based on the type of solid that it's given. So the solid is NH3. And NH3, we know that it's a gas. Okay. So now it's asking, if it's a gas, let's go with the temperature. Which one does a change in temperature affect the solubility of NH3? Well, it's a gas, and if we ever forget, we're going to go on table G. NH3, what do we see? Where is NH3? It's right here. Let me just highlight it. There is NH3. Does the change in temperature affect the solubility? Yes, as the temperature increases, what happens to the solubility? It decreases. So does a change in temperature affect the solubility? What is the answer? Yes, it does. If yes, at which temperature would NH3 be more soluble? What is the graph of a gas like that one? So when would it be more soluble? At a lower temperature or at a higher temperature? Let's go on table F, let's see it. Where would it be more soluble? Where there is NH3. It would be more soluble, look, 90 grams of NH3 dissolve in 100 grams of water at 0 degrees Celsius. But as the temperature increases, the solubility decreases. So if I go back over here, where would it be most soluble? It's going to be more soluble at the lower temperature. And the lower temperature is 32 degrees Celsius. Does a change in pressure affect the solubility of a gas? Well, this is a gas. Yes, pressure affects gases. If yes, at which pressure? Well, what do we say? At the highest would be more soluble, at the highest pressure, 1.8 atmospheres. LiNO3 is a solid. Does the temperature affect the solubility of the solids? Yes, because the solubility of a solid as the temperature increases has a positive slope. Which one is least soluble? Read. Well, least soluble is going to be at a lower temperature. Which one is the lower temperature? 40 degrees Celsius. Does a pressure change have an effect on the solubility? Well, it's a solid. Pressure has no effect. At which pressure would be least soluble? No effect. It doesn't affect. It's going to be the same at any pressure. CaBr, it's an ionic compound. Ionic compounds are solids. Sorry. This is ionic. And this is molecular, and it's a gas. It's ammonia. Okay. Does the temperature so if it's a solid, does the temperature affect it? Yes. The higher the temperature, the greater the solubility. So which way is it more soluble? At a higher temperature, 75 degrees Celsius. Does the pressure have effect? No, it's a solid. Pressure has no effect. Carbon monoxide is molecular. It's a gas. Does the pressure affect? So if it's a gas, we see that the temperature, as the temperature increases, the solubility decreases. So does the temperature change affect solubility? Yes. At which temperature would it be least soluble? At the highest temperature. Which one is the highest temperature? 303 Kelvin. Does the pressure affect? Yes, it's a gas. Pressure affects. At which would it be least soluble? At the lowest pressure at the lowest pressure, 2 atmospheres. Let's move on the next page. On to the next page, whether something is going to be soluble or insoluble. Now, if they give you a specific chemical, you have to go to table F. And let's go to table F. Actually, there's table F, and let's zoom. Okay, now this is what I want you to do on your table F. I want you to circle the word soluble. So these are soluble, but they have exceptions. The exceptions are making them insoluble. So I want you to write insoluble on the exceptions and circle it. Then these are what? Insoluble, and the exceptions make it the opposite. So they make it soluble. So group 1, they're always soluble. Ammonium, always soluble, no matter what. It doesn't have any exceptions. Nitrates, acetate, hydrogen carbonate, chlorate. Now, however, if you have sodium, like chlorine, bromine, or iodine, and these are combined with silver, lead 2, or mercury 1, if these combine, then these are no longer soluble, but they become insoluble. Sulfates are soluble unless they are combined with any of these that they would make them insoluble. These are insoluble, but group 1, these exceptions make them soluble. Okay, it doesn't write. Okay, so let's go ahead and see on the next book, on the next. So let's see. NaCl. NaCl is over here. We're going to go to table F. So let's go to table F. Na. Na is a group 1. No matter what, it is soluble. But let's say you don't see it over here and you see the Cl. Cl is usually soluble unless it's combined with Ag, Pb, and Hg2. Well, it's not. Therefore, NaCl is going to be soluble. So NaCl is going to be soluble. And my pen now doesn't write. Let's go to PbBr2. PbBr2, let's go back to this reference table. PbBr, there is the Br. Br and Pb, they're combined. So usually it's is soluble, but now it's with Pb. That's going to make it insoluble. Therefore, this one is going to be insoluble. And I don't know, let me see if I can write. So I cannot write for whatever reason. So it's gonna be verbal. So this is soluble, this is insoluble. Calcium sulfate. So let's go back to calcium sulfate, to table F. Sulfate, I see that it's over here. And it's usually what? Soluble. But when it's combined with calcium, it becomes the opposite, insoluble. So therefore, calcium sulfate is going to be insoluble. Let's go to NH4NO3. NH4NO3 is over here. We're going to see the NH4 always soluble and the NO3 always soluble. Therefore, it's going to be soluble. Okay, let's go to number 32. Number 32, MgCO3. We're going to go back to our reference table. And we are going to go over here and we're going to have MgCO3. We're going to see the carbonate is over here. That makes it insoluble. Is Mg over here? Well, Mg is not a group 1. Mg is a group 2. Therefore, there are no exceptions. That's why MgCO3 is going to be insoluble. Insoluble because of the carbonate. How about K3PO4, potassium phosphate? Let's go over here. We're going to see phosphates are over here. Phosphates are insoluble unless they are with a group 1. Well, is K a group 1? K is a group 1 if we are to go, it's potassium, it's a group 1. Therefore, this group 1 will make it soluble. So that's why this is going to be soluble because of the group 1. Calcium hydroxide. Let's find hydroxides. Hydroxides are over here, and hydroxides are insoluble. Unless they're combined with Ca, that will make it soluble. That's why calcium hydroxide will be soluble. Lithium hydroxide. Lithium is a group 1. So hydroxides are insoluble, but lithium is a group 1. Therefore, lithium hydroxide is going to be soluble. Lead sulfate. Let's look at sulfates. Sulfates are over here. And sulfates are usually soluble. But when they're combined with lead, lead-2, what is it going to be? Insoluble. So that's why lead sulfate is going to be insoluble. Number 36, ammonium sulfide. Well, we know ammonium is over here. Ammonium, no matter what it's combined with it, it's going to be soluble. Lead nitrate. We know nitrates. Nitrates, no matter what they're combined with, they're going to be soluble because they're over here and they have no exceptions. Let's go to number 38, potassium chromate. Potassium is a group 1. Group 1 metals from the periodic table, they're always soluble. Now let's move on. So now let's move on to the next part. Hydration of ions. What happens in water when I add lithium bromide or MgSO4, magnesium sulfate, or ammonium nitrate? So I'm going to draw that. So let's say I have water. And I add, the first one that I add is lithium bromide. So what happens is it breaks down to lithium plus and Br minus. Now, what do we know about water? Water is a polar molecule, okay? Oxygen is more electronegative. It has an electronegativity of 3.4, while hydrogen has a 2.1. That's why it's a partial negative and hydrogen has a partial positive. Make sure you show that partial, that delta, otherwise they're going to assume that it's ionic. So now that I have these and these, how is water going to orient itself? Well, opposites attract. the negative bromide is going to attract which end of the water? Think about it. This is negative, and these are the hydrogens that they're positive. So which one is going to be attracted to the hydrogen? Or you can show it like this, because opposites attract. How about the lithium, the positive ion, is going to be attracted to the negatively charged oxygen? Now, how about MgSO4? Mg forms Mg plus 2 ions and SO4 minus 2. We're going to change the color of water. What do we say water? Think about it. Water looks like this. This is negative. This is partial positive. Okay. So therefore, opposites attract. The negative is going to be attracted to the positive, which is the hydrogen. And you can see the water orienting itself like this. Or you may see the water like this. Remember, you can see the water like this. And how is this one? It's, well, the oxygen is going to be attracted. Or you may see it like this. And then the next part, that was the MgSO4. Let's do the last part. And the last part was ammonium nitrate. It's going to break down to ammonium. If you ever forget, go to your table E and nitrate. And we know that water is a polar molecule. The oxygen is going to be attracted to the positive ion, and the hydrogen is going to be attracted to the negative ion. And that's the end for pages 53 to 55. I hope it was helpful. Write down the notes and come with questions next time I see you. Be good.